Hello. So this week we learned about functions and templates and arrays and vectors in C++. Before we dive into this stuff, I think it's beneficial to learn a bit more about how a computer works. So some of the reasons of why this stuff is important kind of makes sense. So to make a computer, these are all the parts you really need. This right here is for a gaming computer, and I'll walk you through the parts. So this is a CPU, and the CPU is kind of like the brain of your computer. It's what does all the calculations, all the mathematics, and whatnot. So whenever you have a program and you run your program and it does calculations, all of these calculations are done on the CPU. And if you're familiar with words like Intel, AMD, Core i5, Apple M1, A16, any of those words, those are all processors. And the processor needs working memory so it can store data, store variables and whatnot for it to do calculations. And that type of memory is called RAM. And here we have 32 gigabytes of RAM. You may have seen like computers have RAM when you buy a laptop, like 8 gigabytes, 16 gigabytes, 32 gigabytes. And this RAM isn't where your files are stored, but this RAM is where like your computer uses it like for working memory. It's kind of like when the computer has to do calculations, it temporarily stores data here. So it can access it fast and then use it to perform whatever operation you want it to do. But RAM is a bit different from storage. A lot of people get confused with memory and storage. Storage is something you find in a hard drive, like a storage is like a terabyte SSD, 500 gigabyte hard drive. This is not RAM, this is your storage. So on your storage, what kind of lives there is things like your operating system, your files, your documents, your music, your video, your photos, your games, etc. So these types of files don't actually live in RAM, and they do live on your storage. And the reason why computers have two different types of memory, even though both of them store information, is that one is much faster than the other. Storage is really slow, but it's really big and it's cheap. So for example, here you have 2 terabytes of storage, which is 2000 gigabytes. And I can buy 2000 gigabytes of storage for about $140. However, if I wanted to buy RAM, which is 32 gigabytes, so this is 0.032 terabytes, that much storage cost me $70. So if I was to double this price, 64 gigabytes of RAM would cost me about the same as 2 terabytes. And the reason why RAM is so much more expensive is because RAM is a lot faster. A lot faster. Like multiple thousands of times faster than your storage. So essentially, here is where your files live, and here, this is memory for your computer to perform its calculations. And knowing what RAM is or memory is going to be pretty important in this course. So it's good to kind of have that background knowledge. A computer really just needs a CPU and memory to really do its operations. And then the rest of this stuff is just stuff that helps it. So the motherboard just like connects everything together. The video card, this one's for gaming. It's what processes your graphics to play games. This one is not really needed, it's optional. A case is what you put your computer parts into. A power supply is how you plug your computer into the wall and give everything power. An operating system is like where you install Windows or Mac OS, and then a monitor, a keyboard, a mouse, etc. But essentially, what we're going to focus on is memory and CPU, but like mostly memory. So memory, when it comes to the computer, is 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 kind of broken up into two main categories. The two main categories are called the stack and the heap. So you have something called a stack, and you have something called heap. Um, we will cover this later on, and I don't know too much about it, but I'll tell you what I do kind of know. So a stack, the reason why it's called a stack is it's it's kind of like a jar of memory where like things are like loaded in. So you have one stack, two stack, and three stack. And it kind of goes on forever, or like however big the stack is. And the way that I view the stack in your memory is that whenever you want to run a program, your operating system, your OS, so for example, Windows or Mac or Linux or whatever have you, the whenever you want to run your program, and also your program lives in your storage. So your .cpp file takes up space on your hard drive, and this is in your storage. So this file right here doesn't actually live on RAM, it lives in your storage. And when you load it up and you calculate it, I mean you process it through your CPU starts to put it into the memory so it can start to perform whatever operation you want. Because as I said, the memory is very fast and it helps your CPU it helps so your CPU can work fast and run your application fast because like I said, your storage is very, very slow. So whenever you try to run a program, the way that I think it works is that your program your program needs a memory to run in because your computer has to load the code in the CPP file and put it into memory. And I believe it puts it into a memory called a stack. So every program gets gets like a certain amount of memory called stack. And I believe that each stack is actually like 1 MB or something like that. I can actually verify. Let's check. How big is a stack? 1,000,000 bytes. So 1,000,000 bytes is about 1 GB. Mega, it means million, and bytes. So about 1 MB. So this stack memory is where your program is loaded. So you basically, for example, your int main function, the main function whenever you write your C++, um, has something called a stack frame. And basically, this gets loaded and your program runs. And then if your program needs a more memory, it will start to put on other stack frames. And you might be wondering, okay, so your program loads up into memory and it gets put into something called a stack, and then your main runs in the stack. So what is heap? Well, the way that I understand heap is that heap is kind of like it's kind of like a place for your memory for your program to ask the operating system like, hey, I need more memory. Can you give me some? And that's where it fills it up in the heap. Because remember how the stack is like limited to 1 MB? The stack is really like the working memory of your program. And the heap is where your where your RAM can store, where your program can store extra information that it needs later on. So your heap is really, the way that I understand it, is you have like about, let's say you have like um 4 GB of RAM. So your heap is what helps your program access like these 4 GB of RAM. And these 4 GB of RAM have something called like memory addresses. So kind of like a map, like your RAM is like mapped out. So if it wants to access Like let's say, so that's actually what like a round stick kind of looks like. It kind of has these like, it's kind of like that. And like each of these squares has some level of memory. So for example, this might be 1 GB, this might be 2 GB, 3 GB, 4 GB. And if your program needs some room to store its data, your operating system will give it some data from any of these locations. But because all of these sections are separate, they all need memory addresses. So your program knows where to look for that memory. So just like how you have an address on a map. So for example, if you live, let's open up Google Maps. So here's a map of like Vancouver. Think of think of your city as kind of like a space in memory. And every single house has its own address where you can kind of store information on, or you can put things. So your computer needs memory addresses, just like how you need addresses to send things somewhere or to take things from somewhere. So if you wanted to go to Langara and then go to your house, you would need the address of Langara and you need the address of your house to be able to send things back and forth. So that's what memory address really function as. They're kind of like segments on the map where like the address tells you where to go. Um, the address tells you where to go to basically like read information and to write information from those two places. I hope that makes sense. Anyways, um, so yeah, so like the heap basically gives you access to more memory, and the heap also persists um, beyond the stack, I guess. Uh, well, what do I mean by that? Is that when you, so actually, I should probably talk about that a bit later because functions are a bit different. Hmm. Yeah, actually, I'm not sure. Let's try to see. Heap is not persistent. It is allocated dynamically and then deallocated when the memory terminates. Okay. Um, what is the difference between okay, automatic, structure, dynamic, deallocation, stores memory data structures, sort then syntax must be done manually. Yeah, okay. Um, yeah, so your heap gets cleared whenever your program terminates, but your stack is automatically managed um, by your by the compiler, whereas a heap you are in charge, where like you can manage this. For example, so if you have classes, um, things that persist after a function runs, and things like that, those persist in the heap, and these can be used by any one of these stack frames. And also, this is where kind of like pointers can come into play, but I'm going to avoid using terminology. So that was a little tangent aside. Um, let's focus on what a function is now. So a function in C++ or any programming language is basically an algorithm. So this program is called Algorithms and Data Structures. And functions are basically an algorithm. So what an algorithm basically is you have an input, which you input to the algorithm. You then have the algorithm right here. And then the algorithm runs, and then you're going to output. So that's basically, so this box in the middle is basically an algorithm. And algorithms are everywhere. I would argue that we are basically living, breathing algorithms. When we talk to each other, when two people are talking, this person is talking, and what they say gets inputted into our ears. Then our brain does the computation to process what they said and to think of something to say, and then we output information. And then the same thing over here. So algorithms are essentially everywhere. And in programming, this is basically the basic definition of what an algorithm is, and a function is an algorithm. So what I mean by that is a function. So kind of like math, a function has an input. It does some computation, and then it does an output. So for example, let's say my function is a power function. So this f of x, what it does x squared. So let's say I input 4 into my function. So what this will do is take my input and then square my input and then output 16. So that's essentially what a function is in mathematics, and a function in programming is basically the same. A function can be broken down into those three things. So a function a function first has a name. So I'll call it my function. The function takes in an input, which we can define as anything. So if you want to take in a number, you can call it int input. And then the function returns something. And we can choose whatever it wants to return. It could be a Boolean, an integer, a double, or anything else. But let's do int. So this is essentially the three basic things you need to have a function. You need a return type, you need a name, and you need some parameters. And to call a function, you would use your main function, which we write when you do int main brackets, curly brackets, and then we do return 0 at the end, and in close brackets, and then we write whatever code we want here. So all C++ codes has this, and this is the output return type, which is an integer. This is the name. The main function doesn't really take in any parameters, but it does return something after it's ran successfully. So that's what a function is, and the reason why we use functions is functions enable us to reuse code. So for example, if I wanted to make a function that does get max, I don't have to copy and paste code. I can just wrap it up in a function and call it wherever I want. Oops. So let's try coding. So first we have to start off with with the main function, which every single C++ program has. So int main curly bracket return 0. Oops. So this is all that you need to have a successful C++ program. And if we compile this and we run it, our program runs successfully, but it doesn't really do anything. But this right here is basically a function. And if we wanted to do hashtag include iostream, let's say we want to do some computation, we can do std count world. And then we compile and run it. There we go. So now we're printing something. So our algorithm, takes an input, which is blank here, does some computation, which is the hello world, and then prints it, and then it returns a 0 at the end um, to tell the operating system that the program ran successfully, so it can clear the memory. So when we run this, actually, I wonder if I can copy and paste. So when we run this, can I paste? No, I can't. Okay. So when we run that program, the main function, so a stack gets made, and right, our program has access to the heap, which is all of the other memory we have. So a stack gets made, and then in the stack, we basically have a stack frame for our main function. And then once the main function returns the 0, so once the main function returns something, the main function stack gets popped off. So it basically goes away. And then when the stack is empty, the operating system knows that, hey, the program ran successfully, or the program is done. Now I can get rid of all of the memory that this program needed and then free it up for other programs. So yeah, so that's really what's happening. And each stack frame, so a new stack frame are just these blocks that basically get put into the stack. And the stack frames get loaded in. And the only thing you can do is you can only put things in and then take them out in the order that they were put in. So the only way for me to remove main from the stack is if I took out everything else that's over here first. So stack memory has something called last in, first out. So the last thing that was added to a stack gets removed first. And the main function is the thing that gets loaded in first, so it'll be the last thing to go. And it's often what tells a program that, hey, I'm done now, you can free up the memory and use it for something else. Oh, my thing ran out. Okay. So a stack frame gets generated for each function. So if I wanted to make a new function, and let's say it's a max function. I would want to justify the return type as to be an integer. I'm going to return it, I'm going to call it max. And what it's going to do, it is going to take an integer, a, and it's going to take another integer, b. And here, I can declare two integers. So I can name it int x is equal to 5, and y is equal to 10. So what our max function will do is it'll find out which number is bigger. So first, so now I have to write the algorithm for the max function. So the algorithm is k, given these two inputs, let's do some computation and return the proper output. So I can use an if statement. So if a is bigger than b, then I'm going to return a. Else, I'm going to return b. So what this is saying is like if the first number passed in is bigger than the second number, so for example, if a is 5 and b is 10, so if a is bigger than b, then return a. If not, return b. So what I can do to call the function is to use the function header. So I can do max, which is the name of function, and my function expects two parameters. And when you're calling the functions, they're called arguments. So here's telling me, hey, I need to put in two parameters or arguments. So I can do x and y. And then it's going to return an integer, so I have to store the integer. So it'll be an integer, so I'll be int ants equal max xy. And what I'm going to do is I'm going to print the answer. So now if I compile this, it tells me what the bigger number was. And if I was to change this to 15, and if I was to change this to small numbers, it'll always tell me what the bigger number is out of these two. So what's really happening here is that my main function is running, and then my main function calls my max function. And then when my max function is called, it gets popped into the stack or pushed into the stack, and the max function runs. It has two integers, a and b. And everything here is given a copy. So it's basically information is fed in. So information from my main is copied over into my max. So it has copies of the variables a and b. And then it does some computation, and then it produces an output. And then once the output is made into my main, and then once the function ends, this max is popped off, and then only my main persists. And then once my main ends, my program is terminated, the stack is empty, and then yeah, the computer is like, okay, the program's done. So the reason why I spent so long talking about stack and heap is that it's important to understand that this is what's happening, because it'll help to explain copies and references. So And like I said, that this function gets it gets a copy of x and y. So if I was to do here, let's say remember that x is a in this. So if I was to do a equals to 10 and dy is equal to 20. Oh, it's yelling at me because it doesn't know what y is. So here, b. If I was to do b is equal to 20, and then I was to run the function, and then I was to also print out x and y. You will see that because it was done by copy, even if I assigned a x to be 10 and y to be 20, it will still print out 1 and 2. So here's the 1 and here's the 2. And this is because the memory is copied over. If I wanted to refer the memory, meaning I actually wanted it to actually modify these two numbers, I'd have to use something called an ampersand. And this will actually make it so that these values are actually changed. So rather than having a copy, so rather than a stack, having a copy, it actually has a link to the main function. So rather than, so when the max function comes in, rather than the max function just grabbing a copy of the data, the max function actually gets a link to the actual variable that was called. So my main function has an x. So my main function, rather than it just having an x copy, it basically gets a x reference, which basically means that the this a actually points to the same memory in the location as this x is x stored in. So in my actual like RAM, which is over here, so when it's done by reference, the variable a, when you modify a, it's actually pointing to the same memory address that x lives on. So whenever we modify a here, it will actually end up modifying the x in our main function. So rather than having a copy of the data in a separate memory address, the a actually points to the same memory address that's found in main. And we do that by using the ampersand to tell it, hey, I don't want a copy. I actually want you to use the same memory address as we have for x. So basically a has become a reference to x. So we're able to actually modify x in our main function, in our max function. So now, because I have the ampersands, I should see 10 and 20. So here I get 10 and 20. So basically this is actually modifying x. And this is modifying b. And this is done through the ampersands. So also one other thing to know here is if I was to, let's say, have this max function below my main, just like this. In Java, this is fine. Like in Java, what the compiler will do, and also I should probably try to explain what the compiler is kind of. So we have a so remember how I said that we have a CPU. We have our memory, which is our RAM, and we have the storage. Cool. So our storage is where our .cpp files are stored. So this gets loaded into the CPU. But the thing is, like, you have to understand that the CPU doesn't speak English. The CPU is like a math machine. It does all of its calculations in binary, like ones and zeros. So how do we convert our English, which is if, max, integer, all these words, into something the CPU understands? Is we use something called a compiler. And the compiler, what it does is basically translates English, so basically like the C++ English, into ones and zeros to basically tell the computer, to tell the CPU what it actually needs to do. So for example, when you do x times y, this will be translated into, hey, like read the variable x, then it sends a certain command which tells it to multiply to do all the mathematics that it does and multiply it by the variable y, and then store that multiplication answer into something else. So the compiler is doing all of the heavy work for us to do something as simple as x times y. It's basically converting this into ones and zeros and like the machine code for our CPU to actually do the multiplication. And people who write compilers are people who really understand computers extremely well, because they're translators that can basically speak the human language and they speak the language of the computer, and they're able to actually instruct the computers. So when we're programming, thanks to the hard work that the people who wrote the compiler do, we can actually program using English rather than speaking the language of the CPU, which is like all these like ones and zeros and these load, store, delete, multiplies, etc. And the RAM is again where the CPU can store information temporarily. So for example, if you wanted to do x times y, it could store the data for x, store the data for y into the RAMs, and then it can actually try to compute what the like multiplication is, and then store that multiplication into the RAM and then give it back to us. So that's what the compiler is. So when we use G++, so G++ is the compiler. So we call the compiler and we tell it to compile our project name. So whatever we want it to call, like project.cpp, it basically, G++ will translate CPP into this machine code that the CPU understands. So yeah, that's what the compiler does. And the compiler, in the case that I was talking about, goes here line by line. It goes from here. It says, okay, where we are going to include IOStream. So it starts to load up all of the code that like IOStream has, so we can do stdkout. And then it goes for main function. And then it puts this into RAM, puts this into RAM, And then it goes here, and it's like, hey, we have something called max, but the C++ compiler is like, hey, actually, I don't know what max is. And it freaks out, and it's like, yeah, there is like nothing else that I've read that tells me what max is. It doesn't belong in iostream. It like isn't defined here. So yeah, I don't know what you want me to do. I'm just gonna give you a warning and then exit. So if I was to G++, which is the compiler teaching, here it gives me that error. So the compiler is telling me error use of undeclared identifier. So it's saying like, hey, what's max? Did you mean fmax or something? I don't know what you're talking about. So what we need to do in order to tell the compiler like, hey, this max is actually from my max function, is that we have to tell the compiler before the main that we actually have a function in here called max, and I want you to actually like look at this and try to run it before you give me this error. So in order to do that, we have to do something called prototyping. And how we prototype is we basically just copy the header of the function, and that's it. So if I was to just do that, it will not work. So there we go. So my program now works again because I've now prototyped the function. So now when the compiler runs, it can go here, like, oh, we have a prototype for max, and I'm gonna look for a function that has this header. It finds this header, it reads my algorithm, and now it understands what to do when it gets to this line, and it's like, oh, max. Oh, I know max. It's from here. And what this does is it wants me to go here and do this operation and then return it and do everything else. And then it returns 0, and then the memory's cleared and everyone's happy. So that's prototyping. And that's something you have to keep in mind because C++ does that. You have to declare a prototype or actually just have your function before your main. And yeah, so that's basically instancing. So let's say we want to have a max, but we wanted to do a max for other stuff rather than just integers. So let's say we wanted to wanted to have a max function for doubles. So normally what you would need to do is you would need to, okay, well, because this only takes in integers and returns integers, I will have to make a new function for double. So what I'm going to do now is I'm going to make a new copy, call it max. It's still going to return an integer because that's fine. But now I have to make it handle a double. So now it's going to handle a double, and now I have a max function for doubles. How about characters? Let's see, I wanted one for characters. See which character is actually like a higher value on the ASCII table. I would have to do this and make it char and make this char. Okay, let's say I wanted one for float. Okay, I have to make one more copy. I have to do float. Then I have to do float. Okay, let's say I want a max function for something else. Okay, now you see how I'm having copies of the same code again and again and again. This becomes pretty unreadable and pretty annoying. So to solve this, we use something called function overloading, which actually, so what I was doing here is actually called function overloading itself. And overloading essentially means that the name the name is overloaded. The name is carrying extra load. So this max now does multiple things. So this max can handle double. This max can handle an integer. This max can handle a char. This max can handle a float. So this function is now overloaded. This function is carrying a lot of weight. This name is carrying a lot of weight and it can do multiple things. But because when we do function overloading, we end up getting a lot of copies of the function. If we can, there should be a nice way for me to not have so many copies and just have one copy that's able to handle all different types of inputs and then return me whatever output I want. So for that, we enter into something called templating. And what a template does is template basically, actually I probably should forgot to update this function templating. So basically, what templating does is templating allows us to not have so many copies of the same function, and instead allows us to make one function that can handle a generic type of argument. So how we use a template is we basically type in, I think it is template, then we do, actually I forgot the syntax. Template C++. Hurry up, Gemini. Okay, template type name. Yeah, so template type name, and we can name it T. And now what I can do is rather than having an integer, I can just do T. So it can take a, oops. So now it can just take a generic type, and that type is by reference, and I'm now calling it A. And it's giving me a warning like, hey, because I changed the method signature, I have to make sure that my prototype knows what to access. So I'm just gonna do A. Also, technically, I don't have to do the, oh, also this is complaining because it doesn't know what T is, because I have to actually copy this here too. So that should work. Also, for the prototype, I actually don't need to include the variable name. I can just do this. That works too, but I prefer to include the variable name. So, oops. So it's like more readable. So now I have a generic type name. So now this T is a generic type, and I can pass in any input I want. So I can make this a double. I can make this a char. So I can make this 1.0, and I can make this A. And now what it'll do, well, actually the char won't work. I think I can, yeah, I think they have to be the same type still. Yeah, so I can make this a double. Well, what this will do is this will just convert it. Anyways, so I can make this a double, and this a double, and this will now be able to handle double stuff. So 1.0, 2.0, oh, this is because I'm modifying it. Probably print out the answer first. Oh, actually it won't work because I'm modifying it anyways. Okay, I'll stop modifying it. Cool, let's just clean up. Cool. So this was able to handle doubles. It can handle floats, integers. I wonder if it can handle a char. Let's see. Okay, which one's bigger? 90. So it returned the ASCII code for Z, which is 90. And I can actually store this as a char. So it should print Z. Yeah, cool. It told me that Z was bigger. Yeah, so that's what templates are. And templates helps us to avoid unnecessary overloading by allowing us to pass in a generic parameter. And this ampersand lets us to point back to the reference and modify it. So yeah, that's basically functions and templating. And functions are basically the algorithms that we need to, basically the basis of algorithms in this course. So every single algorithm you write will essentially be a function. It takes in an input, does some computation, and produces an output. Okay, so that was functions and templates and memory. So now let's move on to algorithms. I mean, data structures, because this is a data structures and algorithms course. So we just covered some algorithms. Now let's move on to the data structures. And one data structure that most people are familiar with is arrays. And an array, just like from Java, is essentially a way for us to organize data into a structure. So it's essentially one of the most basic data structures. So I'll briefly draw what an array is like. So array is essentially like a list. And what it is like you can make an array and give it a size. So let's say we can array that size 5. So one, two, three, four, one. 1, 2, 3, 4, 5. Cool. And we can store any data we want, and we can declare that when you make the array. So we can make this an integer array, a character array, which is what a string is. A string is just an array of characters, like that, or any other type of array, really. So that's what an array is, and arrays can have multi-dimensions. And what I mean by that is like arrays have indexes, so just like how a string has an index and a length. So the index array is like 1, 2, 3, 4. So this is index 0, 1, 2, 3, 4, and the length of the array is 5. So we can move to one index and then look for data within that index, and that index might have another array. So it's basically a nested array. So here we can have access to more arrays and more data. And these are called multi-dimensional arrays. And I personally find this a little bit unintuitive. Some people like to think of in shapes, like like array. A simple array is like a 2D thing, and then and then a 2D array is like a cube, and then so forth. I find that confusing. I don't like it. What I like to think of arrays is kind of like a folder structure. So what I mean by that is, let's say you want to make some folders. Cool. So here, so this is my array folder, and I can make a bunch of folders. So this is an array of size 7. And then within these folders, I can have more folders. And then within another folder, I can have more folders. So now I have folders in folders in folders. And this is kind of like how I like to think of an array. So for example, if you want to go to index 1, which is this, we can go here. And then here we can read whatever data is here. So here we can do like We can make a text file, like any type of file. We can store integers, doubles, characters, anything we want, really. So yeah, that's an array. Um, and that's how we view the array, really. So yeah. So let's make an array. So we can remove all this stuff, go back to our main function. And I think an array, you might have import something, or maybe not. And how we declare an array, so let's Google it. Array declaration, let's see, plus. But first, let me try to guess it. I think it's int, then these square brackets, and let me name it int int array, then equal to, okay, yeah, that's not working. So let me search up int. So data type, array name. Oh, okay. So this is flipped. So it'd be data type, array name, that. Okay, so now I have an int array. So what's this yelling at me? Complete, incomplete, type int is not allowed. What? Oh, it wants me to declare size. Okay, cool. Yeah, so here we're making an integer array. Here, actually, I'll just name it array. So int array, and I'm gonna give it a size 5. So what this is doing is, also these arrays are like stored on the stored on the stack. So what that really means is that this array will be stored within here. And then one beautiful thing about arrays is that it's basically, in terms of how it's stored in memory, it basically allocates like so when you declare the int, so for example I did int array 5, it's basically allocated, so an int we know is like, I think it's like how many bytes? I think it's 1 byte. How big is an int? What is that? 4 bytes, let's see, plus, should be 4. Yeah, 4 bytes. Okay. So it's allocating 4 bytes. So we're essentially allocating 4 bytes that are right next to each other. So this is 4 bytes, this is 4 bytes, 4 bytes, and 4 bytes. 1, 2, 3, 4, 5. And this is 4 bytes too. And this is actually right next to each other in our memory. And the beautiful thing is about these arrays is that essentially when we try to read an array, because the memory is right next to each other, it's actually very fast to move forward and backwards within an array. I'm actually not sure. And I think if it's a multi-dimensional array, what happens is like, if it's like a multi-dimensional array of integers, it ends up being like 4 bytes, and then it's multiplied by however dimensions they are. So the data is still next to each other, it's just that the data is larger. Anyways, the data being next to each other is benefit because it means that reading data from this array is extremely fast because it's right next to each other. Like imagine if you were a mailman and you had to deliver packages to houses, and rather than the houses being like scattered around, or like one house is there, one house is there, one house is there, one house is there, and then you had to go there, go here, go here, go here, go here, go here, go here. What ends up happening is like your data is stored right next to each other, so it's really easy to to like read and write, read and write, read, write, read, write, read, write. So that's one benefit of having an array. It's just that all of the data lives right next to each other. But there's also downsides to that, which I will show you. So let's say we wanted to, so here we have generated an integer array of size 5. And now let's say we want to print out what's in the array. And to do that, what I can do is I can make a function. So let's call it, let's say it doesn't return anything. So that's void. Void means doesn't return anything. And let's call this function printer. And let's say that what this function takes and is an integer array. Okay, cool. Actually surprised that worked. Okay, so now, and then it also needs integer, and we'll call it size. So what it's going to do is going to be for each, so what I'm going to do is do auto. So whatever the array type is, for each element. And actually, I think if you do for each, it should be auto. I think we might need this. So if you use a for each loop. So a for each loop is like a for loop, but rather than looping until a certain condition is met, like looping a certain number of times, we basically loop for as long as we have data. So I'm going to do for each element E, and so I'll call this A. Can I pass in? And okay, what I'm trying to do is I'm trying to make a loop. Okay, how to pass an array to function C++. Does not allow you to pass an entire argument. Oh, what? Okay, yeah, that's what I'm trying to do. Int ARR. Oh, okay. Gemini is telling me one thing. Okay, I'm gonna name it AR. Okay. Then I have to. Oh, there's warning me still. Okay. Okay, let's see if this works. SCD code. Gonna print in print E. Then I'm gonna introduce a space. Then after it ends, I'm gonna end the stream. Okay, let's see what it says there. Okay, I think we might not be able to use a for each loop. It's for okay, this should work. Okay, I'm not really sure why this. Why is this red? Oh, okay. Wait, hold on. Could I do for each here? So for each element. Will this work? Let me try to compile. Yeah, okay. Yeah, that won't work. Okay. So you can't do a for each loop for an array, but you can print out this way. So this is my printer. It basically, so this is my printer function. So this is what it takes in. This is the name and doesn't return anything, but it does print to console. So what I can do is I can do printer array. And then see what happens. Int array equals 5. It's because of naming conflict. Okay, how come I can't declare too few arguments? But I do declare the array here. Oh, crap. I forgot that it wants a size. So, okay. Okay, let's see if that works. Okay, so it just printed off a bunch of random numbers. And this is because it just prints off whatever memory was already left over. So kind of like how we had the problem when we declare a variable, but we don't initialize it to 0, it'll just print whatever leftover data was there. So the same thing happens to array. So if we want to initialize the data, we can tell it what we want to initialize it with, and we use these curly brackets. So do this. Cool. So now our array is initialized to 0. And if I even want to change the order, I could do 1, 2, 3, 4. And then last one should be 0 still. Cool. So yeah, so that's an array. And it's basically reading data that's right next to each other. But let's lie about the size, and let's say the size was 10, even though array is only 5. So let's see what happens once you go beyond 5. Cool. So what ends up happening is our array is only size 5, so you have 1, 2, 3, 4, 5. So this is proper, and then it keeps on reading the memory that's right next to it, and it starts to print out these random numbers because this is out of bounds for the array. I think, and that's what happens when we do this type of checking, but I wonder if we can, wonder if arrays have an add function. Um, no, not JavaScript. Array function, no. Sequence, no. What? Okay, member function size. At. Yeah, it should have a add function. AR. Hmm. Yeah, let's see what Stack Overflow says. Yeah, this is a for each. Yeah, it's over raw arrays. Yeah, we use array class. Okay, so I think that's std array. We're not using std array, we're just using the bare bones arrays, and that one doesn't have an add. Okay, cool. Yeah, so yeah, that's kind of an array. And if you want to make a multi-dimensional array, we specify, so there's 5 rows. There's 5 elements, and each element will have 2 sections. And then this, let me see what it says here. Okay, let me see it. Cool, so this requires 2. Okay, why is this complaining? It does. Is there a space here? No, there's not. Okay, let me try to print this. 4. I'm gonna hard code it in. Okay, let me see if this will work. Should print, okay. Error has incomplete element type. I am passing it in. Yeah, oh, maybe I haven't declared it properly. Okay, spring, yeah. Oh, it has to be comma. So, oh, it's nested. Okay. But I am declaring a 2D array. I'm not sure why this is complaining. Oh, wait. No, that's fine. Yeah, it's a 2D array. Um, I guess you can't use it with functions. Print 2D array into function. Okay, I think this stuff is making me use pointers, which I can't. I don't. Oh, I think it. Yeah, I think it needs to know. I think I have to stack functions on top of each other. What? So I can't leave it blank. I can't pass in a function. Can't pass in a. Can't pass an array like that. But if I was to like do that. Okay, so that works. Let's see what it prints. Okay. I'll make everything 0. Hmm. Um, so it has 2 elements, I think. Oh, this is because of the size. Okay. So if I was to make this 5 and this 0, it should still print out 0 because we're accessing 2. Okay. So I, okay, what's it printing out here? Hmm. Hmm. Okay, this is getting a bit complicated. So how many elements is this? One, oh, okay. So the first element's 5. Okay, then it's gonna print out 1, 2. Then this is the sec. Okay, okay, so I have to break this down. So 1, 2, 3, 1, 2, 3, 1, 5, 6, 7, 8, 9, 10. Okay, so the first one, and the rest of them are 0. Okay, so first element should be 5. Then I'm going to make the second element 2. Make the second element 0 and 3. Make the second element 3 and 4. Oh, okay. Now, now it should print that, and rest of them should be 0. Yeah, 5, 2, 0, 3, 3, 4. Okay, I guess, yeah. Okay, anyways, so that was just me playing around with 2D arrays. Um, I would, what I would work around this is I would do like, if I want to print out the entire array, it's like void. Well, actually, no, this is printed. This is printing out the entire array. But if I wanted, yeah, I would do like something that let me increment this. I guess yeah, I guess it needs a size. I'm not really sure why. Why does it need size? The size of the second dimension must be specified. Why? Why in C, why does the second dimension of the array must be specified? C is concerned with actual memory size. Knowing this, it doesn't know how to access elements of an array. Okay. Okay, that's interesting. That's for C, but I guess it's the same thing for C++. Okay, this is a pointer talk again. Okay, maybe I should learn pointers now, because I feel pointers keep coming up. Okay, well, anyways, that's that. So I guess that's arrays. Um, so we've covered arrays and how they're kind of like folders within folders. Actually, I wonder if there's a um, yeah, this should work. I wonder your tree. Yeah, tree should work. Okay, let me do cls cd downloads cd folder tree. Yeah, it doesn't know what tree is. What? I have to install something to show a tree? That's lame. The Windows can do this. Bro, really? You're gonna make me install tree? Okay, is it done? Okay, I hope so. Okay. Okay, can use tree now. Okay. Oh, what was did I delete everything? Let me try to do. Okay. Cool. Yeah, so yeah, kind of just view arrays kind of like this. So we can access the indice. So for example, like this is element 0, 1, 2, and then here we can access other elements, and this can have more elements within inside it. Yeah, cool. So yeah, those are arrays. And like I said with arrays, we kind of have to declare the size at the start. So if I was to, let me see if I can undo. Okay. Okay, that should work. Okay, so the thing with this is that I have to declare the size up front. I can't resize or do anything with the array because the thing is like this array lives in something called stack memory, and the stack memory is fixed. So if I want to have a resizable array, we use a class called vector. Oh, it's yellow. We use a class called vector. And vectors are basically just, it's basically a class that wraps around array. So it's basically arrays, but there's a bunch of niceties just wrapped around them that give us extra functionality, such as being able to resize, being able to shrink, grow, push in information, take out elements, and things like that. So yeah, so now we're going to cover vectors, which are arrays but better. But before we go in, so arrays are stored in a stack. Because a vector is a class, it'll be stored in something called a heap. And so I have oops. So I have a heap vector. So it'll be stored over here. And this will persist until our program terminates. So the beautiful thing about objects that are stored in the heap is that they don't persist for as long as the function does. They will persist after a function terminates. So even if my function was done and I go back to the main, my vector data is still there as as assuming that there's still like a pointer to it. So vector, let's try to import one. Okay, think we have to do hashtag include vector. And what we can do, I think it's this. Let's see this. Okay, how do I declare in a vector? std vector. Yeah, so we have to use std vector, then the type name, so int. And we can just like zero it out. Oh, and we have to give it a name. Cool. So here we actually didn't have to do anything. We don't have to declare the name or anything. All that we can do is we can just pass it in. And then actually this doesn't even matter. So here I'm gonna change it to specs vector b. Okay, as long as okay, so here we can do the for each. Oops, didn't mean to do that. Okay, let me see. I can do pass vector into C++. Oh, I have to specify what type. Would that work? Okay, that worked. Cool. So here we can do a for each for auto e in v out, and then this. Oh, I want to do v. So print each element in the vector, and yeah, this should work. Okay, I have to change into documents case. Okay, never use spaces. Don't be like me. Come on. Wait, what's it in? Oh, okay. Okay, there we go. Okay, and that's going to be cleared. Okay, so it doesn't print anything because my vector is blank. But if I fill it up with 0, 1, 2, 3, 4, 5, 6, it should print. Cool. Cool. Yeah, so I just declared my vector. using, so I declared a vector like this. So actually what I can do is I can declare a vector with just element 0 and then get to print out. Cool. And then what I can do is I can actually make this printer and then I can have it add numbers to it. So let's say I'm going to make a size parameter, or actually let's do 100. So what I want to do is I'm going to start off with a vector that has nothing in it, and then I'm going to keep on adding 100 numbers into it. So what I'm going to do is I'm going to use a for loop. Int I equals 0. I is less than limit I plus plus. Going to implement a limit. The limit's going to be int. Cool. So vector has this function called, so with vectors, we can, if you want to add something, you have to do push back. So we are pushing it to the back of the vector. So I believe that's what it's called. Let's see, that's vector push. Yeah, push back. Okay. So how that kind of works. So how pushback works is, so we have a vector, and a vector is just an array. And right now it's 0, it has nothing in it. So when you do push back, we're telling it like, hey, we want to push in new information into the back of the array. So push back, push back, push back, push to the back, push to the back. So that's what I'm going to do. It's going to start off at 0, going to push 1, 2, 3, 4, 5, and it's going to go all the way up to 100. So yeah, so that's the pushback function. So what I can do is I can do v dot push underscore back I. Okay, what's that? Okay, cool. So this vector, actually what I'm doing is gonna make this vector as one element. I'm going to make it blank, and then I'm gonna print it. So let's see if this works. Cool. So I pushed it all the way back, and I'm feeding in numbers, and here we have an off by 1 error, so it has to be less than or equal to, and then it should give me 100. Cool, there we go. So yeah, I made a vector, and it tells me how many elements there are, and it also has another function that lets me also get the size std out. So with arrays, remember how we couldn't get size? Size? So it will also tell me the size now. Yeah, it's 101 elements is the size. Actually, this is a bit confusing, so I'll comment this out. Oh, oops, I didn't want to comment out that. Oh, no. I mean, I didn't want to comment that print. Cool. Yeah, that's the size. It's 101 elements. Cool. And yeah, that's basically vectors. Vectors are essentially resizable arrays, and they live on the heap. So meaning that even after the function ends, um, they can, they still, they still persist. Okay, I should do a better explanation of that. Okay, so let's separate this function into two parts. So let's make one part writer, and that will take up the 100, and this will just print. So what we'll do is we'll call this writer, and we'll make it so that this, all that this does is it just prints. It doesn't print the size. Okay. And this has to take an int. Oh, I messed them up. So this is right. And this now becomes my writer. And this actually doesn't print. Cool. So, and has to take no size. 100. Okay, so what I've basically done is I declare the vector. I'm going to send it to this writer function, which will basically push these numbers into the vector, and then I have a printer function, and it is then gonna start to print what is in my vector. So let's see if that works. Okay, so as we can see, what ends up happening is my writer function seems to write, but my printer function doesn't print anything, and that's because what's happening here is that everything by default, when the input to the function gets copied, it isn't a reference. So remember the ampersand symbol that we use to reference? So we don't have any ampersands. So the vector, so this vector, v, what it does is when it's passed in, it basically makes a copy of the vector, and then it basically pushes back into that copy. And then once this function is done, the stack frame deletes it. And this work is lost. So when I try to print the function, it basically copies in the vector that wasn't even modified and then tries to print everything in the vector, which is blank. So the way to fix that is to use ampersands. So if I do and, let's see if it does anything. Cool. So as you can see, by just making one difference, by just putting an ampersand, it'll actually start to print out everything. That is, it will make sure it doesn't copy. In fact, it just refers. And yeah, I think that's about it. I think that's all that we learned in functions. Yeah, so we covered functions and templates, and we covered arrays and vectors. Yeah, so basically how you add stuff to a vector is you use a pushback. And vectors are just like arrays, but they're resizable. And vectors are classes. So, and they come from the standard library. And the vector also has functions like this. I mean, methods, which the array doesn't. So that's how, so if you don't need a vector, don't use a vector because it's stored on the heap and it's slow. But if you need So basically, vectors, I don't want to say that vectors are arrays but better. Vectors are better than arrays in many ways because of the flexibility, but arrays still have their place, and the arrays have the speed benefit that I talked about. And because arrays are stored on a stack and they're sequential, there are some benefits to it, but in most cases, we'll end up using vectors just because the flexibility is quite valuable. And yeah, so that's so these two things are data structures, and these two things are algorithms. Well, template isn't really algorithm, but functions are algorithms, and we kind of learned about RAM. Yeah, so that's all that I have. Okay, bye bye.